All right, so in this video, we're going to talk about flow and circulation of a vector field. So if you have a very specific vector field, let's say velocity field, then the flow integral, it's going to be the line integral. So you have the integral along the curve C of f dotted with the unit tangent vector ds. This is the flow integral. And in simplified form, we write this, the integral along the curve C of f dotted with dr. That's the simplified form of this integral. And to evaluate this, if C is parameterized by some curve R of t, and R of t goes from, t ranges from A to B, then this integral can be written as the integral from A to B of f of R of t. So you evaluate the field at R of t, and you dot it with R prime of t dt. So that is our flow integral. Now for circulation, the only condition we impose is that the curve C has to be closed. So if C is a closed curve on our field, then the integral, so we're gonna put a closed right around the integral symbol like that, so indicating this is a closed curve, integral of this closed curve C of f dot dr is gonna be circulation. And it's the same definition as the one you see right on the flow integral. So that's how these two things interpret differently depending on the curve C. So let's suppose F is a field given by this. It is a velocity field of a fluid flowing through a region in space. We want to find the flow along the curve R of t, which is given as that, as t increases from 0 to 2. Right, so we know that our flow integral, it's the line integral along the curve C of f dotted with dr, which is same as writing the integral from some A to B of f of R of t dotted with R prime of t dt. So we need to find what is f of R of t is and what is R prime of t is, and we do the dot product. And these are the limit of integration for t. All right, so let's go ahead and do that. So first we're going to find f of R of t. So here is f. I'm going to write it in vector form. So this is equal to a component y. So the first component is 3xy. Then the second component is 10y. The third component is 1, just a constant. Then if I want to find f of R of t, well, I'm going to plug in R of t component wise into f. But before that, let me go ahead and write R of t component wise like this. So R of t is equal to, as you're given in the problem, it's right here. So the x component is t. So this is t. The jth component has coefficient t squared, and the kth component is just a constant. So now we're going to make the substitution for x, y, and z into our f. So now f of R of t, now that's going to be, so x is going to be replaced with t, y is going to be replaced with t squared, and z is 1. So we have 3 times x, that's t, times y, that's t squared. That's our first component. Then we have 10 times y, y is t squared, and z, there's nothing to substitute, it will just be 1. All right, so that's f of R of t. Now the next thing you want to find is R prime of t. So find the derivative of this guy right here. So that is going to be R prime of t. Component wise, you take the derivative of t, that's 1, t squared, that's 2t, derivative of 1 is 0. All right, now we're ready to do the dot product. So once you have figured out all of these pieces, we are going to take the dot product. So we're going to look at the integral from A to B. So your limit of integrations are right here from 0 to 2. So this will be the integral from 0 to 2 of f of R of t, which is this right here. So we're going to replace that in our integrand. We have 3 t times t squared, that's t to the third. And then the y component is 10 t squared, z component is 1. And we're going to dot this with R prime of t, which we have right here. So this is going to be 1, 2t, 0 dt. So we're integrating respect to t. Okay, so now let's go ahead and do the dot product. So we have the integral from 0 to 2. So when you do the dot product, you multiply component wise and you add them up. So that's how we do the dot product. So 3t cubed times 1, that's going to be 3t cubed plus now 10t squared times 2t, that's going to be 20t to the third plus 1 times 0, that's going to be 0 dt. And you can combine these since they're like terms in the integrand. So we have 0 to 2, the integral of that. 3 plus 20, that's going to be 23t to the third. And that's what we're going to integrate. So using the power rule of integration, this is equal to 23t to the fourth over 4, evaluated from 0 to 2. Now we plug in the upper limit of integration in place of t. We have 23 over 4 times 2 to the fourth minus 23 over 4 times 0 to the fourth. And of course, this is 0. So all of this simplifies to just 23 times 4, which would be 92. Here's another example for you. We are going to find the circulation of this vector field around the closed path consists of the following curves. So every time you're looking for circulation, remember we're looking at a closed curve. So we have a closed curve, and the curve consists of these curves. So we're going to be integrating along C1 and then along C2 and then C3, we add them up. So we know that our circulation, it's going to be the integral around this closed curve, C of f dotted with dr. And this is going to be the integral along C1 of f dotted with dr plus C2 of f dotted with dr plus C3. So this is C2, C3 f dotted with dr. So that's the setup. So we're going to figure out each of these pieces and then we're going to add them up. That's going to represent circulation around this closed path. Okay, so let's start with the first one. So C1. So our focus is going to be on this curve right here, which is this path right here. So we're going counterclockwise if you're viewing it from above. So let's go ahead and do the usual. So we're going to find, so this is going to be for C1. So our field is given. So I'm going to write it component wise like this. So you have 3x, 8z, and 2y. So that is the field we're given. And R1 of t, so that's the curve describing C1. This again, component wise, this is going to be cosine of t, sine of t, and t. And t is going to go from 0 to pi over 2. So we're given the parameterization of the curve C1. Okay, so we need to find R prime. Let's go ahead and find that. So R prime, it's going to be negative sine of t, cosine of t, and 1. And then we're going to find f of R1 at t. So I'm going to evaluate each of these components in place of x, y, and z. So that will be f of R of t. So let's go ahead and do that. So f has the component 3x, x is cosine. So we're going to use 3 cosine of t. And then the y component, well, it's going to be 8z. So that's going to be 8t because that's our z for R of t. And 2 times y is sine of t. So because that is y and R of t. All right, so that's our f of R of t. Now let's evaluate. So the integral, so we're doing the first line integral along curve C1 of f dotted with dr. This is going to be the integral from 0 to pi over 2, because that's the bound on t, of f of R of t. That's going to be 3 cosine of t, 8t, and then 2 sine of t, dotted with R prime. R prime is right here. So this is going to be negative sine of t, cosine of t, and 1 dt. All right, so a bit tedious, but we can continue on. So let's go ahead and do that. So we perform the dot product. We have the integral from 0 to pi over 2 of, so I'm going to do this times that. So you'll have -3 cosine t sine of t. And then I'm going to do 8t times cosine of t. That's going to be plus 8t cosine of t. And then the last term, we're going to do 2 sine t times 1. That will just be plus 2 sine t dt. All right, so that's what we get after we perform the dot product. And now we break it up into 3 separate integrals so that it's easier to work with. We have the integral from 0 to pi over 2 of -3 cosine t sine t plus dt. The integral from 0 to pi over 2 of 8t cosine of t dt plus the integral from 0 to pi over 2 of 2 sine of t dt. Okay, so the first integral, we can do it by using simple u substitution. You can pick u to be either sine or cosine. Now for convenience, I'm going to pick u to be cosine, so the derivative would be negative sine of t dt. So now if you integrate, you're going to get u squared over 2 and replace u as cosine. So this will give us 3 cosine square of t over 2 evaluated from 0 to pi over 2. And now the second integral, now here you have t and cosine t. That needs to be done by parts. We're going to do that on the side. Let's integrate that by parts. So we are going to integrate t cosine of t dt. So you'll have to pick u and dv. So u is going to be t, and dv, I'm going to pick that to be cosine of t dt. So then du is going to be dt, and v is going to be sine of t. So this integral is going to be u times v t sine of t minus the integral of v du. So that would be sine of t dt. So hopefully you remember how to do this. Now this integral is going to give us t sine of t. Integral of sine is negative cosine, so that will throw with a negative. You'll have just cosine of t plus c. Now since we do have limit of integration, we're not going to tag along plus c. So we're going to go ahead and replace that here. So our integral for this second piece, it's going to be that. So that's what I'm going to replace right here and multiply each of pieces by 8. So you'll have plus 8 times t sine t, and then 8 times cosine t evaluated from 0 to pi over 2. And the last integral is pretty straightforward. We know the integral of sine. It's negative cosine. So this is going to give us negative 2 cosine of t evaluated from 0 to pi over 2. All right, so let's continue. So let's plug in the upper limit of integration for each piece. You'll have 3 over 2 cosine of pi over 2 is 0 minus 3 over 2 cosine of 0 is 1. For the second piece, we do the same thing. Plug in pi over 2 for each t. We'll have 8 times pi over 2. Sine of pi over 2 is 1 plus 8 times cosine of pi over 2, that's going to be 0. Now the lower limit we subtract, so 8 times t is 0, and then minus 8 times cosine of 0 is 1. And the last integral, we have -2 cosine of pi over 2, we know that's 0, so this is going to be 0, and then minus plus 2 times cosine of 0 is 1. All right, so we see that this is 0, this is 0, this is 0, this is 0. So this will give us the following value. We have -3 over 2 plus 8 pi over 2, that's 4 pi, 0, 0, and then minus 8 and plus 2. So the value of this integral is going to be -3 over 2 plus 4 pi minus 6. All right, so that's along C1. And that's what I'm going to replace right here. So our first integral gives us -3 over 2 plus 4 pi, and the last piece was minus 6. Okay, so now we continue to work and find this integral and that integral. All right, so here's how this is going to look. So we're going to find f of r of t. So that's going to be Now let me write R of t this way. So you have R of t, or this is R2. That's going to be component-wise. The ith component is 0. The jth component is 1. The kth component is pi over 2 times 1 minus t. All right, so that's that. And also the bound for t is from 0 to 1. So we have our field, f of r of t is 3 times x. X is 0. 8 times z. So that's going to give us 8 times z is pi over 2 times 1 minus t. And then 2 times y, y is 1. All right, to simplify this, you will have 0 and then 4 pi times 1 minus t. And then 2 times 1, that's 2. Okay, and now let's find the derivative of R2. And then we're ready to do the dot product. So this is going to give us the derivative. So I'm going to take the derivative of this. Derivative of 0 is 0. Derivative of 1 is 0. Derivative of the next piece is just negative pi over 2. All right, so now we're ready to integrate. So the line integral along curve 2 of f dotted with dr is the integral from 0 to 1, because those are the values on t, of f of r of t dotted with r prime of t dt. And we have each pieces. We're just going to perform the dot product. So this is the integral from 0 to 1 of f of r of t. That's 0, 4 pi times 1 minus t times 2 of 2, comma 2, dotted with r prime of t. That's going to be 0, comma 0, comma negative pi over 2 dt. All right, so let's do the dot product. This is actually pretty straightforward. So the first two components are going to be 0. So we're only integrating 0 to 1 of the component 2 times negative pi over 2, which will simply be just pi. And then if you integrate, you're going to get negative pi. All right, so that is our value of this integral along C2. Pi, so we're going to replace that underneath. Now we need to finish up one more integral, which is this one. So I'm going to rewrite R3 in this way. So R3 of t is equal to, so the ith component has t, the jth component is 1 minus t, and the kth component is 0. So that means f at r of t, or R3 of t, is equal to, so I'm going to plug in t for x, so you'll have 3t, z with 0, so it'll be 8 times 0, that'll be 0. 2 times y, that'll be 2 times 1 minus t. All right, and then we need to find the derivative of R3 of t. So derivative of this guy right here respect to t, that would be 1, negative 1, and 0. And now we do the dot product. So we will have the integral, the line integral along C3 of f dotted with dr is equal to the integral from 0 to 1, because those are the values for t, and f of r of t, so that will be this component right here, dotted with r prime of t. So hopefully you got the idea how we're doing this. This is 3t, 0, 2 times 1 minus t. And we're going to dot this with r prime, that's 1, negative 1, 0, dt. All right, so the dot product is also pretty straightforward for this path. So we have the integral from 0 to 1, 3t times 1, that will be 3t. And then 0 times negative 1, that will be 0. So, and then the 2 times 1 minus t times 0, that's going to disappear too. So we're only integrating that. And this is pretty nice. This is 3t squared over 2, evaluating from 0 to 1. So this will give us, if you plug in 1, you will have 3 over 2. If you plug in 0, you get 0. All right, so we got 3 over 2 for the line integral along C3. Positive 3 over 2. So now if you sum these up, you have 4 pi and a negative pi. That's going to be positive 3 pi. And then 3 pi, 3 over negative 3 over 2 and 3 over 2, they cancel each other, minus 6. So our circulation around this closed path is going to be 3 pi minus 6. Okay, I hope this makes sense. Hopefully you had a good time working out these problems. I'll see you guys next time. Take care.